So today we have Ben Webster, who will tell us about twisted traces and symplectic singularities. Take it away.
All right, thank you. Ooh, okay. So I just wanted to give kind of a general warning. I think most of the people in this crowd are from sort of the physics world. I'm not originally from the physics world. I, kind of have picked up a bit of the lingo from hanging around at PI, but there might be some moments where I'm like, oh, I don't know, Davide told me this was true and I believed him. I don't know how to explain it. I kind of use this picture often because, oh, no, sorry. I think I said the wrong corner. This is definitely where I'm living right now, where I'm standing in front of the physics blackboard, looking at it and feeling confused. Oh no, it is. Yeah, it's this side. That's right. This is the people in the mathematics department looking at the Feynman diagram, going, what is this thing? All right, but I do occasionally learn things from hanging around at PI. So I think I have something to say in the talk. So the kind of physics that I, ended up interested in because I was sort of doing the mathematics that corresponded to it on the other side is 3D quantum field theories with n equals 4 supersymmetry. And I've gradually learned that the reason I'm interested in these is they have two topological twists. Right? The n equals 4 supersymmetry gives that to me. If I had less than 4 supercharges, or I guess I should say 8 supercharges, then I wouldn't have any topological twists. So I need this much supersymmetry to get topological twists. But there's this kind of cool observation that there isn't just one way of getting a topological twist, there are two. And when I look at the local operators in those topological twists, those give me commutative rings, which are the chiral rings of the Coulomb branch and the Higgs branch of the theory. And physicists would say these are half BPS operators. There's kind of two natural classes of them, which are protected by these two different topological twists. So are there any questions about that? I want to sort of say, I don't know exactly what everyone's background here is. The names I recognize, I know are sort of more on the physics side. So please stop me if I go by something too fast. And at least I'll have a chance to say, I don't know, I heard that somewhere, but I don't know why it's true. Okay.
I think for now it's good.
Good. So these rings have garnered a lot of attention in recent years, and sort of how I ended up in this quantum field theory business was I was kind of interested in the kinds of spaces that come up as spectrum of these commutative rings. And the case where we sort of have some hope of getting a mathematical handle on things is when your theory is gauged hypermultiplets. So a gauged sigma model into flat hyperkähler space. So in the Coulomb branch chiral ring, in sort of an important special case, so when you have one of these flat hyperkähler manifolds with a compact group action, there are sort of two possibilities. One possibility is that you're the cotangent bundle of a complex representation. Oh, apparently I'm giving myself a thumbs up. Or you might not be. And somehow that first case is much simpler and will usually be the one that we'll think about. So in that case, Braverman, Funkelberg, and Nakajima gave a very nice mathematical description of what the Coulomb branch chiral ring is. And I didn't write this here, but maybe I should mention, from the physics perspective, Gaiato, de Mofta, and Bullimore sort of came to somewhat similar conclusions, but had a slightly less precise formulation of exactly what you get. Whereas it had been calculated much earlier by Hitchin and some collaborators that the Higgs branch chiral ring is a Hamiltonian reduction of the holomorphic functions on E. So from the perspective of spaces, you're doing a hyperkähler quotient, but there's a way to describe that in terms of these chiral rings. It's basically, you mod out by a complex moment map and then take invariance for the action of your group. So that's a sort of Hamiltonian reduction. All right. So, what I was interested in was these spaces. And it came as a real shock to me to learn that these spaces, which are called symplectic singularities, tended to come from 3D n equals 4 supersymmetric field theories. And so once you learn something like that, you start thinking, well, what other information is there in the quantum field theory that I haven't learned yet, right? So it's sort of cool to learn, okay, I'm interested in the nil cone in type A, the space of nilpotent n by n matrices. Oh, that turns out to be the Higgs branch and actually the Coulomb branch of this quiver gauge theory. Well, that's interesting. What could I learn by looking further into this quiver gauge theory? And well, if you're just looking at the algebra of local operators, there's sort of a piece of information that you're missing, which is you don't learn anything about correlation functions. And well, if you talk to physicists and try to get them to explain to you what a quantum field theory is, like the first thing they'll tell you is that you have a bunch of operators and there are correlation functions between them. Like that's what the quantum field theory is, at least according to certain people I have talked to. So it's a little weird that on the mathematical side, we don't have any of that information at all. We've completely forgotten. So what I'm, slowly working on trying to understand is how do we bring some of that information of the correlation functions over into the mathematics and think about it as an object we can understand. Okay, so I have these topological twists. I think about I've got my big complicated 3D quantum field theory. I have a topological twist. I look at the protected operators for that. That's supposed to give me a topological quantum field theory. But for mathematicians, that's a very upsetting claim to make. Because, for example, the local operators, that's the Hilbert space assigned to an S2 in the usual kind of mathematical formulation of TQFT, that's infinite dimension. If you tell like a mathematician who like read Atiyah's book that you have an infinite dimensional vector space assigned to the S2, they'll get very upset right away. And they'll say like, oh shit, that's not dualizable, blah, 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 blah. So sort of there's something a bit like bad here about this theory from the perspective of like TQFT that mathematicians like. So if I were in that world and everything were finite dimensional and life were very simple, I would say, oh, correlators, that means that I have a three sphere, sort of taking two balls and gluing them together along the two sphere on the outside. My trace is that I could take a local operator, insert it on that three sphere, and I would get some number assigned to that by the TQFT. So that's kind of the picture I would like to have, and which obviously I can't have because somehow my TQFT is like too infinite dimensional and integrals don't converge or something. But on the other hand, supersymmetry kind of rides to the rescue. Things can kind of be saved and I can get some interesting information. So because I'm in 3D and I have n equals 4 supersymmetry, I get this very interesting picture that I'm still kind of processing because I was sort of reading papers about this to try to prepare for this talk and realized like somehow this was a little different from how I thought about things. But the superconformal algebra in this picture, right? I'm actually bringing in something extra here, which is quite often this 3D theory will have a superconformal IR limit. I think it's IR, not UV. I don't know. Ulysses, did I get that right? Yeah, okay, good. And so in the background, there's sort of not just, the usual sort of Euclidean structure of having SO3 and then translations. There's actually superconformal. And the Lie algebra of this is OSP44. So in OSP44, there's the even part, which is SP4, which is the conformal transformations of R3 in 2-1 signature. I could complexify and not worry about signature anymore. And SO4, which is the product of two copies of SU2. So the SO4, that's the R symmetry. And somehow where the fact that I have these two different topological twists comes from the fact that I have these two SU2s. And sort of there's an A SU2 and a B SU2. And those kind of correspond to the two different twists. And if you look in these papers, I should, shoot. This is the problem with not having the pen, is it's too easy to draw on the slide. So if you look in these papers of Beam, Pillars, Restelli, and Chester, Lee, Pufu, Jacobi, I knew I was going to forget some of those names if I didn't look. You get sort of natural twists, which are not quite just the topological twists from before, but also incorporate some of the conformal structure. And these come from copies of SU2-2 in the superconformal algebra, which if I were thinking in the complex world where I'm happier, I would say I have C44 with a bilinear form, which is like symmetric on the odd part and symmetric on the even part and anti-symmetric on the odd part. And I look for a Lagrangian subspace in there, which is 2-2, and I look at the subalgebra of the superconformal algebra that preserves them. So on R3, that actually manifests, and I have a line, and I have the conformal transformations preserving that line. So in particular, translation along the line and rotation around it. And a choice of preferred twists that comes from this choice of Lagrangian C2 and the odd C4. So another way to think about these two twists, which is also a way to think about why SO4 is SU2 times SU2, is that if I look at C4 with a symmetric inner product, symmetric bilinear form, there are two kinds of Lagrangian subspaces in there that correspond to the two factors of SU2, and thus to the two twists by A and B. All right, are there any questions about this? I have no sense of whether all the physicists are like, oh yeah, OSP44, we know about that superconformal algebra. What are you wasting our time with? Or, you know, whether this is sort of something weird.
No, it's perfect.
Okay, good. I agree. OSP44 is perfect. All right, so we get a twist that isn't just the supersymmetry. It combines the supersymmetry and conformal transformations. It depends on the choice of a line, which is the even C2, and the choice of an A or B twist, which is the odd C2. And if I take the cohomology of operators with respect to this twist that has a natural structure as an associative algebra, it's no longer commutative because of this conformal part I put into it. But the algebra I get, it's still the same size as the Coulomb or Higgs chiral ring. So what I actually get is a deformation quantization, a star product on the Coulomb and Higgs chiral ring. And where this is coming from is that I also have this conformal rotation around the line. And I'm incorporating that into the twist. So I learned a while back that you should call that an omega background. So you can think of that as giving you this quantization, but it's also actually picking up some protected operators in the conformal part of this field theory. All right, great. And because it incorporates this rotation, you can't swap your 2 points now, right? The reason I got a commutative algebra when I just thought about the supersymmetric twist is that I could move my 2 points around arbitrarily, not changing the correlation functions. And so I could have them swap places. and see that multiplying them in one order, the other was the same. Now that I have this rotation, I can't do that in a way that is compatible with the rotation. They run into each other. All right, cool. So a big part of this quantum field theory is described by this protected associative algebra. And now we should have some expectation values for operators in this algebra. Now, as I said before, if I were thinking about a usual TQFT, I would want to think about, I have S3, and I just stick my local operator into that, and I find the expectation of that. Well, now I have sort of a special line, and I'm trying to do things conformally, but that's okay. R3 and S3 are conformal to each other. I can map S3 to R3 by stereographic projection, which is conformal. And so I can stick that line in S3 and make it into a great circle, or a way I kind of like to think about it is S3 is SU2, and this is a U1 inside SU2. So again, there's some choice of which U1 you want. We mathematicians would call that choosing a carton or choosing a torus. And so now before we had some points on this line, now we're looking at points on a circle, which we can write as e to the 2 pi I theta, where I'm thinking of SU2 as unit quaternions. So, things of the form A plus BI are a circle inside the unit quaternions. And I can look at inserting, that should be O1 and then some other operator ON. I just didn't, okay. Maybe I can actually fix this. So we can take a bunch of operators at a bunch of different points, and we're supposed to have a quantum field theory. So there should be some number I attach to those operators. Now, the other thing that's supposed to happen is if I move my points around, that correlation function could change. And it turns out if I allow my mass and Fi parameters to be non-zero, then actually I will get a little bit of a change when I move points around. So it's not kind of purely a topological picture anymore. Instead, I get a change, but it only depends in this sort of very simple way on the Fi parameter or the mass parameter, depending on whether I'm looking at the A twist or the B twist. For most of the rest of the talk, I'm going to be looking at the B twist, so you're going to be seeing the mass parameter showing up here. All right. So we have these points, we can move them around. Things change a little bit when you move them around, but not in a really important way. We can still have them collide and multiply. But now we're on a circle. So there's another important thing we can do, which is we can have two operators and we can send one around the back and have it come around the other side. So what ends up happening is that when I take the expectation, it's almost a trace, right? So trace you can kind of think of as putting operators on a circle and then doing some evaluation on the whole circle. And it has this cyclic property that I can move things around the back. But I know that I pay some cost when I move things around the back. I'm changing the operator when I do that. So I don't just get a normal trace. I instead get a twisted trace. And what's the twist? Well, I have this term that comes from the Fi parameter that comes from the actual moving things around, the fact that my operators evolve as I go around the circle. This is one of these points where I just say, people keep telling me it's there. I can't explain very well why for you this is there, but signs show up places in physics. That's life. This F this multiplies A times twice its conformal dimension. So this is picking up whether, in the SU2 that acts on the Coulomb branch, are you in a representation of SU2 with half integer highest weight or integer highest weight? I don't think it's actually right to call these bosons and fermions, but it's, the same representation theory of SU2. All right. So when I reorder operators, I don't quite get a trace, but I get a trace up to this automorphism. So this is what's called a twisted trace. And this is what I like to see as a mathematician, because this is an actual precise thing, right? This is a structure that an algebra has or it doesn't have. And I can actually study it and understand what's going on. So this is sort of an extra piece of the quantum field theory, which mathematicians have not really been exploiting when they think about this picture, but which should be in there and should be part of the data of kind of the mathematical stuff you can scoop out from a 3D n equals 4 field theory. Maybe it has to be good and have a nice superconformal limit. That seems to be a condition that keeps coming up. And that was the A twist story. The B twist story is almost the same. So the important difference here is A Coulomb versus A Higgs. What changes, the only thing that changes is that I use the mass parameter instead of the Fi parameter. And this is actually the case we'll be talking about for
Can
most.
I ask a question?
Mhm.
If you turn on these real masses or Fi parameters,
Mhm.
do you change the star product or not? Or can you just pull it out and the star product is the same up to some?
Okay, so the star product, it's always that the star product depends on the parameter that isn't showing up in the trace. So on the Higgs side, the star product depends on the Fi parameter, and the trace depends on the mass parameter. So they're slightly independent things.
Yeah, okay.
The way I always remember this is that it's always that one of them is sort of giving you the actual multiplication structure on the algebra, and the other one is an automorphism. It's, like a flavor symmetry kind of thing. And of course, that's what you need in this twisted trace picture. So somehow, like, properties of the trace, the algebra with the trace, depend on both the choice of Fi parameter and the mass parameter in both cases.
Then
Yeah.
M is taken here to be just a 3-vector.
So M, I was being a little, sneaky about this, right? One way you could think about M is it is itself an element of A Higgs, which then acts, when I write boldface M there, it acts by taking bracket, right, commutator in the non-commutative algebra A Higgs. But it's also that, there's a flavor symmetry that's the moment map of.
Yeah, but okay, so there is a flavor symmetry. There's also the fact there is the R symmetry, and when you exponentiate, you need to be specific about you exponentiate only a singlet, and that's the thing which is not clear to me. Is this this exponential
the
is
thing I'm exponentiating, like on the level of the algebra, is the derivation of, like I can think of M as being in the Lie algebra of the flavor symmetries, and I'm exponentiating that element of the Lie algebra. So this, it's an element of the complexified flavor symmetry group which acts on A Higgs.
Okay, so that's one aspect of it. So that's the flavor symmetry, and there's also the R symmetry, because it's also transforming under the R symmetry.
So it's like in the hyperkähler quotient where you have a triplet of moment maps. You can split them into real and complex. And then the question is, are you taking both of these, or you're taking the real one or the complex one? Like, or the associated level?
The complex one. Like you're
complex one,
thinking
okay.
of the complex moment
Yeah.
map as an element of the chiral ring.
But
Okay.
then you're picking a choice. Then you're picking a choice, right? I mean, maybe you were saying that you're working with holomorphic symplectic variety, and you declare some holomorphic.
Yeah, I'm
structure.
thinking about holomorphic things. I thought that was what chiral ring meant.
Okay, so
Yeah, it's fine. You fix a complex structure. That's okay.
Yes.
okay, so and you ignore the real part.
At the moment, yeah, I ignore it. Maybe I
Okay.
should.
Oh,
I would be interested to understand the real part better, but yeah, I mean, somehow for me, I mean, so one of the parts of this I wish that I understood better, and we keep kind of hoping to find some information about, is exactly this kind of non-holomorphic stuff you're talking about. You know, there's this kind of mystery of mathematicians are very bad at understanding like why there should be pictures in this picture and how to think about those.
I see.
So
Yeah.
why there should be what? I didn't hear this.
Hyperkähler structures.
Oh,
Like
I
why,
see. Okay,
you know,
yeah.
why is there a metric? Like
Yeah, sure.
how to kind of think about this or I mean, maybe I shouldn't say mathematician. Maybe I should just say me.
Okay.
That this is sort of something I'm kind of hoping to see more of in this picture, because, you know, there is definitely some of this SU2 action kind of hidden in this world. But I don't know quite how to extract it yet. Okay, so that's sort of a nice overall picture. How do we actually compute anything? So unfortunately, this is one of the points where I was counting on myself to draw a picture, and then I never got my my pencil back. All right. So the picture I want to draw, I mean, my operators are on an S1. And one way to think about things is if I cut that S1, there should be a Hilbert space, and I should be taking some kind of trace on this Hilbert space. But I want to think about this a little differently, because that's the way I actually understand how to do things, which is I want to cut two ends off of it. So this is, I have my circle, and I cut it into two relatively straight segments, and then two connections at the end. And the way I want to think about this is, well, the sort of cuts, that must correspond to not just sort of the original Hilbert space, but a doubled version of our Hilbert space. The two cups must correspond to some kind of diagonal state, right, corresponding to the identity under the state operator correspondence. And then I can insert operators on these sort of relatively straight parts. So what does this look like in the most simple example? I have one ungauged hypermultiple. So then A Higgs, this is the Weyl algebra. I have X and Y, and they satisfy the canonical commutation relations. So the kind of usual Hilbert space you would think of for this would be L2 of R, with, you know, X and Y acting by position and momentum operators, right? So to double L2 of R, I'm going to look at L2 of C. So if I have L2 of C, then I have holomorphic differential operators. I have DDZ and multiplication by Z. And I also have anti-holomorphic differential operators. I have DDZ bar, and I have multiplication by Z bar. And these guys around the sort of U-bends, I want to think of as corresponding to the Gaussian in this L2 of C. You know, as I've sort of learned a lot of this stuff by talking to Davide, he likes to denote this Gaussian by, as a cat with a 1, and pairing with it as a bra with a 1.
And what's the Hamiltonian? You're talking about the ground state. What's the Hamiltonian?
I mean, this is a topological quantum field theory, so there's no.
So it will be something like XY, maybe quadratic.
I don't think there is a Hamiltonian. Or let me just say there won't be a Hamiltonian that shows up in my picture.
Okay.
Right, like this is a topological quantum field theory. There won't be any time evolution. I mean, maybe the answer is something like the Hamiltonian is the mass parameter, so I get to choose. So yeah, then it would be something like XY.
XY, it looks like it. Yeah.
Uh,
Because you're using here the language of a highest weight or a lowest weight space, and
Right. So there is some hint of this, like the full SU2 there, where I'm looking at holomorphic and anti-holomorphic things. I don't know. It was a big change for me to start thinking about things which are anti-holomorphic as well.
I see. Okay.
I don't have a good explanation of it generally, like where this SU2 is coming in. All right. So the kind of key calculation to kind of see how everything fits together is that when I take a Gaussian and I act on it by ddz, well, I multiply by z bar. And similarly, probably I'm missing a factor of 1/2. I didn't have as much time as I would have liked to prepare these slides, so factors like this kind of dropped by the wayside. But assuming you get all your scalars right, when you do ddz, you multiply by z bar. When you do ddz bar, you multiply by z. And so what this is telling you, I left myself a lot of space to hang myself here, is that when I have these two kind of U-bends, well, I want to act by holomorphic operators at the bottom. So if I put X here, right, then that's the same as putting minus Y here. Right, so I can move this guy up here at the cost of turning an X into a minus Y. And similarly, if I put a Y here, it becomes an X when I move it up. Right? Oh no, minus X. And on the other hand, if I move X and Y down here, they become Y and X. Right? So the holomorphic representation turns into the anti-holomorphic representation. And then it turns back into the holomorphic representation, but I picked up a sign going around the circle. And that's that minus 1 to the F. So if I go all the way around the circle, then my X and my Y get sent to minus X and minus Y. And both of these guys have conformal dimension 1/2. So that's that minus 1 to the F gives me a minus sign here. All right. And this is for trivial mass parameter. If I have a non-trivial mass parameter, I have to sneak in some one of these exponentials of the mass parameter in somewhere. Okay. I don't know. Is this as clear as it's going to be? I don't know. I really like this picture of sort of what this is saying here is if you look at this pairing of the two states on the outside and then pair up with action of either this holomorphic action or this anti-holomorphic action, this will be unchanged as you sort of slide operators around the circle, as long as you properly account for this switching holomorphic to anti-holomorphic etc. All right, so the expectation can be written as a pairing between vectors in here. And you can check here actually on the file algebra, there's only one twisted trace up to scalar, and this is one way of writing the unique one. And if I normalize the pairing between bra and cat correctly, then I'll get the answer I expected from kind of other physical means. One particularly nice consequence of this is I can actually use it to construct a positive definite inner product on the algebra itself, where I define the norm of an operator to be act on this state, the cat, and then look at the norm of that vector in L2 of C. Any questions? So one of the mathematical inspirations for thinking about this stuff was actually getting at these inner products. Because, so, you know, if you're a physicist, you might have said, oh, why are you writing this crazy A Higgs thing? You just mean polynomials in two variables with Moyal star product. And being a mathematician, I get a little uncomfortable with that statement because it's like, well, it's isomorphic to polynomials in two variables with Moyal star product, but it's not uniquely isomorphic to that. Which isomorphism do you want to choose? And having this inner product actually has a nice kind of consequence that it tells me the right isomorphism to choose. Right, I sort of know what I should do up to lower order terms, that when I have some monomial in X and Y, up to lower order terms, it should go to the same monomial in polynomials, and I just have to figure out what the lower order terms are. But I can fix this by saying, well, the polynomials of degree n in real two variable polynomials should be the stuff in A Higgs, which has the right leading order term that's perpendicular to all the elements of order less than n. Right. So what I'm trying to say here is, right, if I think about differential operators, I can't say differential operators which have exactly order n. I can only say order less than or equal to n. Right. And I can use this inner product to say, but you know, things of order n should be perp to things of order lower than n. I promise you this works. And this actually explains why you get what's called a short star product. So if you have three things, you take the product of two of them and take the inner product, using some cyclicity of this inner product, basically the twisted trace property, you only get a non-zero answer if R, S, and T are the sides of a triangle. So that tells you, of course, that T can't be too big, but it also tells you T can't be too small. So somehow you can't get expressions showing up that are too low, which would be an inner product where T is very small and R and S are big, by this, doesn't help to point, by this triangle inequality. And this is exactly what's called a short star product. So this is, I should say that, you know, this short star product property was originally noted in work of Beam, Pillars, and Rastelli. It was sort of mathematically, this argument was written down by Eddinghoff and Stryker, though they gave Kontsevich credit for coming up with the actual argument. All right, any questions? So there's sort of a general argument that whenever you have one of these sort of twisted traces that gives you a positive inner product, then you get a short star product automatically. Okay, well, that's the most basic case, just one hypermultiplet. So how do I get more interesting theories? So like I said, the ones I want to think about are taking multiple hypermultiplets that transform according to some representation of a compact group and gauging with respect to that group. So the first thing I would do is say, okay, I'm going to take more hypermultiplets. Well, I just replace C by higher dimensional complex vector space, which I was calling N. So I would replace L2 of C with L2 of N. That's got a higher rank Weyl algebra acting on it. Everything is simple. Now I want to gauge by the action of a compact group, which I assume N is a complex representation. So what I can do, and this is sort of the answer that we've known for a long time for the Higgs chiral ring and its quantization, is to do a quantum Hamiltonian reduction of that Weyl algebra. So again, I impose the complex moment map as a relation. That's what this part means. I'm modding out by that. And then I take the invariance under the compact group. And that gives me the quantized chiral ring, this protected associative algebra. And you can obtain, oops, I said algebra, but I meant trace. On this reduction by doing an averaging process over the complexified gauge group. You need to be like a little bit careful about this. It's kind of scary because the complexified gauge group is not compact, but actually this integral will converge as long as your theory is good. So if you have a good theory, then this integral is going to converge to a twisted trace on A Higgs. Somehow it's probably not coincidence that this has to do with having a conformal limit in the IR. And if you have some extra conditions, mathematicians like this, if the moment map is flat, and maybe the important kind of physical part of this is that m equals 0 and the mass and Fi parameters are 0, then this trace is going to give you a positive definite inner product on A Higgs for sort of the same reason that it did before. Basically, you can very carefully think about what it would mean to take this Gaussian and average the Gaussian over GC. That's a slightly weird analytic object, but it ends up being a tempered distribution and you can kind of make sense of everything. All right. Any questions? Okay, well, I have a few minutes left. It's a good thing I didn't prepare more than this. So, what do we do with this, right? This is satisfying to me as a mathematician of like, oh, I didn't, I had thought a lot about these, Higgs branch chiral rings for many, I have like now a couple of decades of experience thinking about these things. And like, lo and behold, there's a new structure on these guys that I'd never thought about, which is this twisted trace. So that's exciting for me. It's maybe boring for you guys because you're like, yeah, we knew that conformal field theories had expectation values. Great. Correlation functions. But we did learn some more interesting stuff by thinking about this. So, I should say this is, kind of proven rigorously in our recent paper on this stuff with Davide Gaiato, Justin Hilburn, Redondo Yuste, and Zhou, where we showed that if you have an abelian group, you can take this trace and you can expand it in terms of twisted traces of Fermi modules. So I kind of like to think about this by thinking, oh, if you had a usual TQFT, everything would be finite dimensional. So you would kind of expect that your trace would be a sum of traces on simple representations of this Hilbert space for S2. There aren't any finite dimensional representations for A Higgs, but somehow Verma modules kind of play a similar role. They're kind of a replacement for finite dimensional representations. I should say, there was relatively recent work of Bullimore, Crew, and Zhang, which explained this in terms of hemispherical partition functions on basically taking an S3 and cutting it up as two balls meeting along a two-sphere, they have some picture where you think about different boundary conditions on that two-sphere corresponding to supersymmetric vacua, and you get a sum over those. This is somehow explaining why these coefficients have some other interesting interpretation, because they look like the traces on Verma's not for the Higgs branch, which is what we've been talking about this whole time. This is all for A Higgs, but in terms of the Coulomb branch. The sort of physics perspective on this stuff tells you abelian theory shouldn't be very special. This should work in much more generality, but for abelian theories, you can just do the computations, some contour integral, and you just do the contour integral, and you see that everything matches up. Are there any questions?
Yeah, quick question. So you're in the B twist, right? But so then
This is all in the B twist. Yeah,
it's also in the B twist. Okay.
Yeah.
Okay. Good. Yeah.
Right, which is why it's sort of strange that these Vermas for Coulomb branches are showing.
Yeah, but this is kind of the neat thing of like a twist and boundary. Yeah, kind of this dual picture.
Mm-hmm.
Okay. Good. Thank you.
All right, so what about Coulomb branches? I didn't write this down here because, as I say, especially this part, I was running out of a little time to prepare. So in the abelian case, you can just do Fourier transform, right? I have this guy written as an integral over GC. I can just do Fourier transform of that integral, and it becomes this formula that we already know is supposed to work for the Coulomb branch, which at least I found in a paper of Dedyshenko, Pufu, and Jacobi, where you do this integral over the carton of your operator in your Coulomb branch. This only works for the scalars, but somehow those are the only interesting guys you'd expect to have a trace. You think of that as a polynomial function on the carton, and then you integrate it against this quotient of cinches and coches of the weights. So the denominator is the weights of the representation n, the numerator is the roots of the Lie algebra. And they tell you that this is the right way to compute the expectation. So in the abelian case, this is just the Fourier transform of the Higgs branch formula. I'm currently working with one of my graduate students, Keke Zhang, on which was not the Zhang on the previous slide, different Zhang, on sort of formalizing this in the BFN perspective. That there's a paper of Davide's from this summer that kind of gives you very strong hints of what the Hilbert space you should consider for Coulomb branches is. We're working on kind of writing this down carefully, showing that the BFN Coulomb branch actually acts on there. And so you can get a twisted trace by exactly the same trick of having a bra and a cat and a holomorphic action, an anti-holomorphic action, and sandwiching everything together. But, the details are taking a little while. So we expect to be done with that soon. We'll see. All right, and that's all I had time for. So luckily, both in terms of preparation and in terms of talk. So thanks, everybody. Let me know if you have any questions.
Very good. Let's thank Ben. Questions? Okay, so I can ask a canonical question. How does a stratification show up at all in this story?
Sorry, yes, I had meant, this is one of the things I was kind of hoping to get to. So, one kind of natural way to think about this is if you have a twisted trace on your algebra, then you naturally get an ideal from that, which is all the things A such that the trace of AB vanishes for all B. And because it's a twisted trace, right, this is a two-sided ideal, because when I multiply by something on either side, I can move it around to the other side. So the kind of natural way you would hope to look for the stratification here would be look for interesting traces where that ideal, where the trace is sort of always zero, is the functions that vanish on one of the strata. And what you would expect is that you're going to get all of what we would call the special leaves by doing this. And I have some ideas about how to do this in the Coulomb case, which I just both like somehow this paper needs to get written first before those can really be used. And, I sort of didn't have time to try to even figure out vague explanations of them for this, but I think this should be possible. Somehow if you take a totally random element of your Hilbert space, you wouldn't expect that you could sort of pair and get a twisted trace, but you might be able to take some other ones and get a nice twisted trace by using the same kind of picture.
So if we take, for example, U1 with two hypermultiplets, so the Higgs branch is C2 and Z2,
Yeah.
is this like practical to actually work out like explicitly what these things look like and to see this?
Well, I mean, there, right, like you're looking for a finite dimensional representation. So you know what the trace you're expecting is. It's the trace of the finite dimensional representation. Yeah, I mean, this is somehow one of these things where morally, it really seems like it should work out, but I haven't had kind of time to work out the details. It's a very kind of common idea that, you have some simple for example, simple representations of Lie groups, right? You can write as quotients of Verma modules. And it's actually exactly that you have pairing on the Verma module, which kind of has a tracey kind of flavor. And the stuff you kill is exactly the kernel of that pair. It's called the, shoot, I'm blanking on the name. It's a long Russian name. Shapovalov. Shapovalov. That's what it is. Right. So I'm hoping to see sort of a similar kind of story with these Coulomb branches.
Very nice. Do we have more questions?
Can you just repeat what the C alphas precisely were on the previous slide?
I didn't say very precisely. So what they are is they're the same kind of trace, but okay, I skipped a lot of details here, right? So first of all, when I'm looking for a twisted trace, okay, if I was looking for a trace in the usual sense, I could take any representation or a finite dimensional representation and take the trace of the matrix actually acting on that representation, right? Now, if I want a twisted trace, well, I can't take usual trace of the representation, but I can take trace of the action on the representation times a factor, an automorphism of the representation itself, which kind of makes everything work out. And so first of all, I skipped over the fact that I'm doing that on the Vermas for the Higgs branch, but you can also do that for the Vermas of the Coulomb branch. And if you just kind of do all the computations, what you find is the trace that sort of comes out of the actual quantum field theory is the trace on the Verma module of the Higgs branch times the trace of the identity on a Verma module in the Coulomb branch. And of course, if you did this for the Coulomb branch, Higgs and Coulomb would swap places. Since we're talking about abelian theory, its dual is an abelian theory. So somehow what's Higgs and what's Coulomb is just a matter of perspective anyways.
Okay, yeah, thanks.
Mhm.
That makes sense.
So you want that your definitions will be invariant under the way you construct the space, right? You want to focus on the moduli space and not on its construction. There will be some details which are related to the constructions, but you want that if I construct it once with a Higgs bunch, then there should be some formulation, appropriate formulation with a Coulomb bunch. If
in the abelian case, that's like exactly Fourier transform.
Okay, and so you want that all of those extensions will be consistent with these Fourier transforms.
Well, right. I mean, somehow the interesting thing is, in other cases where there's a duality, like it's much less obvious why it should be the same. I mean, that would sort of be an interesting thing to check in these cases. One understands, of like linear or cyclic type A quivers, right? I don't know why. I don't know if it's true that you get the same traces on those guys thinking of them as Higgs branches and as Coulomb branches.
I see. And you were proposing integrals which are converging. Was there any attempt to get explicit expressions?
Well, I mean, that's what we did in the abelian case. In the abelian case, you have this integral, and you can sort of, you can write it as so here I'm writing it as an integral over the complexified gauge root. But actually, this Gaussian is already invariant under the compact part. So really, I can write it as an integral over the Cartan complement to the compact part, right? There's sort of a natural, like if I were thinking about, GLN, right? I would be integrating over the positive definite matrices instead of the unitary ones, because the unitary ones aren't doing anything interesting. I'm just using like polar decomposition. So I'm now integrating over, and then there's a version of the Weil integration formula, which allows you to write that as an integral over the sort of complexified, the imaginary direction in the Cartan. And then now I'm integrating over a half-dimensional cycle in a complex space, and I can rewrite everything in terms of like I can think of this as like a line integral, and I can use residues. And actually, like honestly, as a mathematician who wants to work out all the details, like one of the hardest parts of this for me was like figuring out what's the right version of like the residue theorem for these kind of calculations. But I think I did finally satisfy myself that we were doing the right thing.
It will be very useful for us to see actual, a quiver and an expression.
Well, I mean, we like if you, I can, if you look at our paper, let's see. Let's see. Well, yeah, maybe this is something we can discuss offline. I mean,
Yeah. I mean, maybe there are other questions.
So are there other questions? Okay, so yes, then maybe I would say let's move off the record. But before we do that, let's thank Ben one more time for this nice talk. And